Okay, so let's look at section 3.3.3, the joint probability density functions, PDFs, lowercase. And here we just define f of x and y as the mixed partial of f of x and y. So partial of x, partial of y. Okay, so for instance, if f of x and y were to equal, let's say something like what could I use? Well, I'll use x times y. And I guess in this case, I think this will work. 0 is less than x and y is less than or equal to 1. So when we get to 1, 1, we get 1 out of this thing, and it's what I'm not sure, I guess it's increasing everywhere. Yes, because it would be a parabola, I guess. Sort of, well, it would have a saddle point. So I'm not sure. We won't wreck a good story with facts, but I'm not sure right off that that's actually a density function. I guess it would be, because when we take the distribution function, but I guess it is. So f of x and y is equal to the second partial of xy with respect to x with respect to y. So partial derivative, we are simply treating the other variable as a constant. So this is equal to, if we do the y first, this becomes then the partial of x with respect to x, and we get 1. Okay, so and this would be for 0 less than or equal to x, less than or equal to, x and y less than or equal to 1. I could also write it as 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 1. Okay, so we just get that function 1, and then we can also write down our distribution function f of x and y in terms of this PDF, and of course that's the probability that x is less than or equal to x and y is less than or equal to y. But for the continuous functions, that's just the integral from minus infinity to x and the integral from minus infinity to y of our f of x and y dy dx. And so for our particular case, we should be able to get our xy back there. So if we say our f of x and y is the integral from minus infinity to x minus infinity to y of 1 dy dx, well, I integrate here, and so that's the integral from minus infinity to x, and that just gives me y. Well, let's see, except it gives you, and actually I should, instead of using a y and an x, Yeah, I don't think this, let's see, so I need a dummy variable here, so maybe u and v. So when I integrate this, I'll get this as y. Oh, I see what I'm doing wrong. I put minus infinity here, but actually, right, there's no support there. It's all 0 until I get to 0, so we'll use zeros there. Put a 0 here. So that is y minus 0. Whew, that was a close one. dv. So that's the integral from 0 to x of y dv. And so then I integrate again, and I just get y times x minus 0. And so that's x times y. Okay. Whew, man, that was a lot of work for something pretty simple. Okay. Let's see. So, I'm just looking here over the end of this to see what's left. And, oh, yeah, just that we can define our f, whoops, uppercase. We can define our f x of x as this is f of x and plus infinity. So that's equal to the integral from minus infinity to x, integral from minus infinity to infinity of f of u and y du dy. Now here use the dummy variable because I've got the x up there, but since these are both limits to infinities, I could just use the y and the y there, which reminds me back here, yeah, see I had the x and the x. I should have written a u and a v back here and a u and a v to keep things a little cleaner. Okay, so that's the idea of a marginal density function. If I wanted fy of y, that would be f infinity y like that. This would be minus infinity to infinity, minus infinity to y of f of x and v dy dx, dv dx. There we go, dv dx. So, okay, so those are the marginal distributions, and there's an example. Example 3.7. And they say a boy and a girl plan to meet at a certain place between 9 and 10. Okay, so we're here between 9 and 10. And each is not going to wait more than 10 minutes for the other. Okay, if all times of arrival within the hour are equally likely for each person, and if their times of arrival are independent, okay, so independent, make a note of that, and all times are equally likely, and they're not willing to wait more than 10 minutes, we'd like to know the probability that they would meet. And so what happens here is And you could use any units you want. The book ends up using minutes. You could use hours. You could do between 0 and 1 hours. It just, it's all in what you want to do. But so sort of when would they meet? And what we have to do is come up with a picture, and that would be helpful. So that picture, if one person comes here, so say we place X, and that could be the boy or the girl, either one. But if that person, right, if X is here, then Y, and let's let this be that same value. So say here's a value K, then here's a value K. Then if we say this person has arrived at K, this other person needs to arrive within 10 minutes, and we'll use their minutes, on either side, like that. And they will meet. And if we were down here, so see, here's kind of the y equal x line, and we need to be within 10 minutes, and at some point it gets squished like this, and up here, something like this. So what we know is anywhere in here is, I didn't draw that very well. Let me redraw that. So there's our y equal x line, and let's say there's our 60, and there's our 60. Then, okay, we need to be within 10 there, and all the way down, and we need to be within 10 here, and all the way up. And so that's what we need. So this distance is 10, that distance is 10. Up here somewhere is 50, over to there, and same thing here is 50. So they need to arrive in here and not out here. And so what that says is I need to talk about how to do this integral. And you all, in the textbook, they say, well, we don't actually have to do an integral, and we'll look at that in a minute. But generally speaking, yeah, we do. And to do that integral, a double integral here, we actually have to kind of split this up into 3 places, because different things happen in each of these 3 places, because what we want to do is just slice it up. Okay, and maybe slice it up along the x's, slice it up, and slice it up. And you've done that in Calculus 1, definitely. In Calculus 2, you should have done some sort of slicing of integral areas, so that's the idea. And so here, notice first we would like x to go from 0 to 10. And when we're in here, what does y do? Well, it goes from 0 up to this line, which is the y equal x plus 10 line. So what we can do in terms of a double integral, and we don't actually have to quite do it this way, we go 0 to y equal x plus 10, and so this would be a dv and a du. Oh, I forgot my f here. f of x, no, uv dv, because that's with the y, because we're saying y equals, and du. Okay, so we need that plus, and now in this next portion, again, if we slice it up, we're going to go from 10 to 50 on the x-axis. And this is going to go from y equal x minus 10 to x plus 10. And that's going to be f of u and v dv du. Okay, so we're just slicing along here and asking what y does on each slice. And then finally, the last piece, the y in that case goes from x minus 10 up to 60. And so x is, when it goes from 50 to 60, y goes from x minus 10 up to 60, and that's our f of u v dv du. So usually that's the hardest part. Now we need to define what our f of xy is. Well, it said they arrive anywhere in here uniformly, or anywhere here uniformly, depending on the person. And so there's a 1 over 60 for each person as to what minute or about where they arrive. They could actually be at the half minute and so forth, but so we get 160, and they're independent, so I just multiply those two together, so we get that. And so that is 1 over 3600, and in this case that's 0 is less than or equal to both x and y is less than or equal to 60. And so now what we would have to do is each of these integrals. And so I can do that first one, integral from 0 to 10, from 0 to x plus 10 of 1 over 360 dv dx. And so that is equal to the integral from 0 to 10, x plus 10 over 360, or 3600 dx. And that is, when I put 0 in there, I just get a v for an antiderivative. I put in the x plus 10 and I put in the 0. 0 disappears. And then here, when we do this one, we'll get x squared over 2 plus 10x all over 3600 from 0 to 10. And when we put that in, again, the 0 just goes away, so we get 100 over 2 plus 100 all over 3600, and that is 150 over 3600. So that's our first region. Now we can go through and do each of those again, but one of the things we notice is, since this is a constant, so the height in here over everything is exactly the same. So it really comes down to, the total height or the total volume is 1. Well, we just need then the volume inside this little piece, and we could get that geometrically, is what they point out. So instead of doing these integrals, we could just say, oh, well, I'm going here, I've got a triangle from 10 to 60, and from 0 to 50 here. So I have a triangle that's 50 by 50 as far as the two legs, and a triangle up here that's 50 by 50. Okay, so that makes a total area of a square that is 50 by 50. So that's the part I don't want. So actually what I want is to take that 1 over 3600 and then I'll do the full 3600, so really I'm taking 1, minus the 50 squared to get my area here, and then the volume when I multiply by that. And so this is 1 over 3600 times 3600 minus 2500, and so that's 1100. So I get 11 over 36 for my result. And I'm going to look down here. Hopefully they got that same thing. They did. Yay. Okay. 11 over 36. Now I did mine by subtracting. They did theirs by adding the 3 areas. And notice when they take their areas, they well, I'm trying to see what they did do. Let's see. They have, I'm not sure. They just say by inspection. So then they do a 2 times 5 times 10 and 10 square root of 2. So the square roots of 2 things are the hypotenuse parts. But I don't know. I'd have to kind of look at their picture here to see. Oh, I see. Okay, so they did it differently than I would have probably found the area. But they did a rectangle and two triangles. Yeah, they look to me like they went about it in a sort of funny way, but they also got 11 over 36. And so that's working through that example, or at least most of it. Again, generally speaking, you need to do these, well, in this case 3, but you'll need to do integrals, double integrals like this. Now, on these double integrals, again, since I sliced the area up, so I'm taking a very long time. I realize that to get through this, but we want to make sure you get the mechanics too. So we had this picture, and what I did was I integrated here first, and I said, well, slice it like this. Now, what you know from Calculus 1 and 2 is that, yeah, you would take the integral from 0 to 10, because that goes from 0 to 10, and then for each slice, you would have written the height here, but the height here is just x plus 10. Okay, now we still would have needed our 1 over 3600, but and then dx. But notice, right, that is exactly what I ended up with right here when I did the double integral. Okay, so double integrals aren't really that scary, but they can be a little rough to put together. But you have done this slicing technique before, and the only difference is that you may, because this function may be complicated. See, with just a constant, I could just put it here. But if it's not a constant, I really do need that double integral going from 0 to 10 and then 0 to x plus 10 of my f of u and v dv du. Okay, and again, I in this case, because that's a 10 and that's a 0, I could have just used an x and an x. Oops, I don't want that comma there. Okay, so, you know, if you need any help whatsoever on these double integrals, just let me know and we'll work on them. All right, so that is the PDF, joint PDF stuff.